All right, threshold signatures. And threshold signatures are valuable because we can use a signature, an R and an S value, to sign for automating the processes inside Ethereum or Bitcoin or other chains. So from the first part of threshold signatures, we have an alpha, which is a threshold ECDSA private key that's been shared between all of our nodes. And we have Y, which is a ECDSA public key. It's public, so it's also shared between all the nodes, but it is public. So we have these these nodes, and they're initialized with this alpha and Y. And we have alpha is the encrypted X, which is the encrypted private key. So although all of them have the encrypted key, none of them know what it actually means because it's still encrypted. But they have the public key. Now, the process of doing a signature, we're going to pick a random value. That random value is somewhere a point on the elliptic curve, and that's what we use in relationship with our key pair to do the signature. Our goal is to produce this R and S signature. Now, it turns out that in most of these systems you have to produce R, S, and a 1 through 4 value that's the quadrant that the signature is in. But if you have the R and S, that is an obvious value at the end. So I'm not going to talk about the quadrant, which is the V value. We're just going to talk about how it generates the R and the S. And throughout this, we're going to do this with distributed and an elliptic curve, so that the nodes themselves never have the information to know what that signature is until the end. So, the signature. So we select this random value. In fact, the way we go about selecting the random p-value is we select a random p-value on each node. So we have p sub I for each node that's selecting the random value. Then we compute this u sub I value, which is the encrypted p-value. That's fairly straightforward, since we're just going to take the values that we have for the previous round, the threshold ECDSA, and encrypt it. Once we have that, we can compute this v sub I value, which is the multiply basically it out to get what this new value is. And each one of the nodes has to have their own v sub I value. Now, given that we have this pair of u sub I and v sub I, we now have enough information that we can actually combine those together and do a zero knowledge proof, just like we did before. The zero knowledge proof can now prove that our original values of alpha and Y are the authoritative values that we're using for producing this. So the combination of these we can now distribute, and we have another broadcast phase where we take this and we say, okay, I've picked this random value and I can show that it has a relationship and everybody can prove it to everyone else. Now, in a real system, do you have to do the zero knowledge proof at this point? No, but it proves the correctness of all of the nodes and that they're participating and not lying. So every node shares its zero knowledge proof. Everyone looks at everyone else's result and says, okay, yeah, everybody that's participating has gotten to this point, and they have all used the correct values. Now, the zero knowledge proof is zero knowledge, so it doesn't actually share anything, but at the end of this, we can combine all the u sub i's and all the v sub i's, which had to be shared anyhow, and we can calculate the u and the v, which is really this piece of stuff over here where we do the calculation. So at the end, we've produced this intermediary setup values u and v. Now steps 3 and 4. Okay? We're going to use the same kind of a commit pattern and the same process, but this time when we get done, instead of just ending up with an initialization and a proof that, everybody used this correctly, okay, we're actually going to end up at the end of this in a final step 5 that is the R and the S that can be used for the signature. So, again, we turn around and we select a k sub I that's a random inside the range of our potential elliptic curve, which is our 256-bit number. So each one of the nodes goes out and does another random number generation. And we select a random integer c sub I, which is the multiplier that we're going to use with the original k value. So they've all got a multiplier, they've all got a point on the curve. Now, we do this computation, which is the r sub I, and remember we're after r and s, so this is each node calculating their own r, which is g to the k sub I, and k sub I is the value that we picked randomly, g is the generator. So we're going to generate for each node its own share of the r value. And then, once we do that, we can take and calculate out k sub I times p plus c times q. And I know this is one of those weird computations, but what we're after is this encrypted w sub I. So we do the calculation on the inside and we encrypt it, and the w is going to allow us to get to the s. When we actually, in the last step, we can substitute some things in and we can get back to the s value from this. And the important part about this w sub I is that because of the way it's calculated as just a multiply and some other things, it's going to allow us to do it without ever revealing what the value is. So what we're after is that they all generate a w in this fashion. The w we can then sum, but what we know is that the sum of w's is equal to the encrypted value. So this is one of the tough steps that takes a lot of computation if you actually implement it. But at the end of that, guess what? We have another pair that we can actually do a zero knowledge proof on. And we can circulate this pair and we can do the zero knowledge proof. And again, they're encrypted, so none of the nodes actually have the actual value. But we turn around and we do the same sort of a zero knowledge proof we did before to show that these values have the correct relationship. And every node knows that they have gotten an intermediary result that is correct with the correct initial values. This eliminates all sorts of problems in terms of communication, because this is the second round of broadcast that we've had to do. If we've got 100 nodes, then it's 100 nodes talking to each other. But we know at the end of this that r sub I and w sub I are correct. We know that we can sum those and we can get the final round. So we've gotten to this set of values that all share together: k, c, w, and r. Okay? Now, the last round, okay, we go through and we do this horrible set of substitutions. Okay? But at the end of this, we have the final value, which, I've got the decode, because I now have enough values to decode the w value. Okay? So we have eta, which is the decoded w value. And eta is, when we do the threshold decode, okay, we can now know that that's equal to k times p mod q. And we're going to use that in some substitutions down here. And phi, the little trident guy. So we also have this other calculation that says that q is equal to k sub 1, or the inverse of k multiplied by the inverse of p. And when we do this set of substitutions, we're going to get back, what is that letter? Okay, now I'm looking at it. I wrote it, but I didn't remember it. And it's not A, it's the other A in Greek. So, silly me, I should have just used letters instead, but here we go. And we've got this little guy right here. And when we do these substitutions, we get down to, yes, that guy, after all these substitutions and calculations, is actually equal to, in an algebraic sense, the encrypted S value. And that's what we're after, is the encrypted S. Because we've got R, because we can sum these things up, and we get the encrypted S. Now, as soon as we have the encrypted S value at the end, guess what? We have the threshold ability to decrypt it, and we have an R and an S value. Now, none of the nodes in between ever were able to see this until the end. And when they're able to see it at the end, we now have a signature that has no way of revealing what the keys are, and the R and S values can be used as a signature. So we've generated a signature in 5 rounds. Okay, the signature is this calculation right here. It gives us the encrypted S value, and that final signature we are now ready to use. And I can walk you through what goes on in round 5, but basically all of these guys are algebraic. We know that we're going to get to this by doing these encrypted calculations, and we have out of this, yes, an R and an S signature, and that's the pieces we use in the signature. Calculating the V value at the end, not this V, but the where the quadrant is really trivial, because once we have the signature, we can just look at the private key component of the signature, which is the R, and we take that piece of the signature as a point on the curve, and we say which quadrant is it in, 0, 1, 2, or 3. We know the probabilities are that it's either in 0 or 1, and 2 and 3 aren't real values because it's an elliptic curve. And there's our signature. Now we can do all sorts of fun things with a signature. Right now, the way that it works if you're in Bitcoin is that a person has to actually use their signature, their private wallet, to spend any Bitcoins. They actually have to be online to sign stuff. But you'd like to be able to build smart contracts that actually do things and run automated. With a person having to sign to spend their money, you can't automate anything. So this gives you the ability to turn around and automate things like Bitcoin transactions and Ethereum smart contracts, where they can actually spend funds from an account in an automated fashion. Every time it generated a random number, also, we can have a round of random number generation that's based on, basically, we set up this process, we do the first part of it, and we use that last value as a random number. So this is going to take multiple calls to the process to build the different pieces, but at the end of it, what do we have? We have keys that are distributed, nobody can see them, and they're not just distributed, they're distributed in a fashion that has high redundancy, because if we have 100 nodes, we can lose a few in the middle of this process and we can still prove that everything is going to work. We have high confidence that this is going to work because we have multiple rounds of zero knowledge proofs in the middle, that everybody is doing what they're supposed to do and using the correct values. And no one, there is no central authority that has one of these values. There are other applications besides just Bitcoin. You could also use a system like this for high-level security, where when a person wants to have security, they have a signature from a system like this that says that, yes, it possesses the key, and then at the end, we do a zero knowledge proof that the person also possesses the same key at the same time. So you've got a private key and you've got a distributed private key. And if they can both do the proof together that they have the same key, we have a two-factor authentication type situation where one factor is from a network and the other factor is from the human being. And we can prove authenticity. So this distributed threshold doesn't just have applications in terms of being able to do the honey badger distribution of data. It also has applications in terms of being able to do security and authentication at a high level. And what I like about it really is the fact that throughout this entire thing, every one of the nodes did their computation on encrypted homomorphic values. They never saw the keys themselves, which means they can't divulge the key because they only have a piece of an encrypted key.